There we go. All right. So for higher derivatives, f just means you're talking about the original function. F prime, this is what we've done so far, means that you're taking the first derivative and when we were talking about these story problems, we called, like the original function could have been s of t, and that's like the position of something. It's like a position that the car is in, it's at a specific spot or whatever. And then the first derivative, we said that was the rate of change for how that thing is moving. So if we're talking about a car, that's how that car is moving. And we said v of t was the first derivative of position. And what does v of t mean? Velocity, right? So that might be meters per second. Right? So the position would maybe just be a unit of meters, like it's sitting at a certain place, like 5 meters away from something. But then velocity is rate of change. That would be like meters per second. That's what velocity is. And then we can actually go past that. We can take the second derivative of something. So that's f double prime. Ooh. That's the second derivative. Does anyone know how you could describe the rate of change of velocity? So velocity is like I'm consistently driving 30 miles per hour. So what's the rate of change of how fast you're like currently driving? I'm currently driving 30 miles per hour. Can how fast you're driving change? Yes. What do you do to make how fast you're driving change? You accelerate or you brake, right? So acceleration is the derivative of velocity. It's how your velocity is changing. And it's the double derivative of the position. All right, so that's what acceleration is. And this would be like we're saying meters per second is how fast you're driving per second. So how many meters per second are you speeding up per second? Right? Kind of weird. So think about it again. If we're driving, how many miles per hour are you speeding up per hour if you're just going faster and faster and faster and faster and faster? Because you're driving at a certain speed, but then you're changing the speed that you're driving at. So you're changing a rate of change. Okay, wrap your brain around that. So they say these units are meters per second squared. Meters per second squared. It's m divided by s divided by another s. So meters per second squared is how we describe acceleration typically. If you're taking physics, you've probably heard that already. Meters per second squared. So acceleration is the rate of change of a rate of change. Okay, how are your brains with that idea? Just think of cars and driving. You guys have experienced this a lot. You're consistently driving at a specific rate of change, then you start to change that rate of change, and that's a double change. Okay. We can also find the third derivative. And I don't have a practical example of a third derivative. The change of a change of a change. I'm not sure what that would look like. And then we can say with the fourth derivative, that's where we start to ditch the Roman numerals. And then we're just going to say dot, dot, dot. We can do this forever. There's a point where you run out of derivatives, though. That's an n for the nth derivative, because some equations are only going to have 3 derivatives, and some equations could have like 17 derivatives. So it depends on the problem. They don't always have the same number. Yeah?
It's like a fractal equation that would have a derivative x to the 5th
would have multiple. X to the 5th would have 5 or 4. We're going to see one like that in a second. Okay. So for our first example, we're going to say find all the derivatives for the equation. Okay, so not just the first one, but all of them. Find all derivatives. For the equation y equals x to the 3rd minus 6x squared minus 5x plus 3. All right, what is the first derivative? Okay, that's the first derivative. Now we're going to find the second derivative. I almost said it with a P. Find the second derivative. Like it's minus 12. What's the third derivative? 6. Are we done? We got one more. Fourth derivative is 0. Notice I put parentheses around the 4 because I'm making sure this is not an exponent we're talking about. This is a derivative we're talking about. At that point, you're done.
Hey.
No more.
I like these problems. These aren't that bad. Can we just have problems
For a
like
polynomial, yes. Other ones where you have like square roots and fractions and stuff, probably not. That's a good question. Right away, probably not. I don't know how far calculus goes within those. We'll have ones that are more difficult than this, yeah. The other types, if you think about like the product rule or the quotient rule, things can get messier, for sure. They can get messier problems. All right, here's another example. All right, a truck enters the off-ramp of a highway. At time equals 0. So we're starting the situation when a truck is getting off the highway, basically. Its position after t seconds, that's a t right there, is S of t is 25t minus 0.3 t to the third. And this equation only works to define the position if your t value is between 0 and 5. So between 0 and 5 seconds, that equation would describe where the truck is located. Okay, so the first question we're going to do is how fast is the truck going? The moment it enters the off-ramp. So, if I'm asking how fast is it going, am I talking about the position of the truck? No, what am I talking about? The velocity. How fast is it going? That's the rate of change, the velocity. I'm not asking how fast it's slowing down or how fast it's speeding up. I'm just asking how fast is it going the minute it exits the ramp, okay? So what am I trying to find? Velocity of t, so v of t, which is the first derivative, right? V of t is the first derivative of the position. So what would you guys get if we did v of t of this equation? 25 minus, what is 0.3 times 3? 0.9. T to the second. Okay. All right, so they're asking how fast is the truck going? What is the velocity the moment it enters the off-ramp? And what's the time the moment it enters the off-ramp? 0. So what do? Plug in 0. So they asked, How fast was the truck going the moment it enters the off-ramp? So they're asking, what is the velocity the moment it enters the off-ramp? And the moment it entered the off-ramp, we look earlier on in the problem at what we wrote down. They said that was at time equals 0 seconds. And so we just plugged in 0. That's it. So we end up getting 25. And what are the units? It says per second, but it doesn't. Other than that, we don't know. So I'm just going to say units per second. You can actually write out the words unit if you think that UN is going to confuse you. So this is unit per second because I don't know if it's miles or if it's meters or what it was. Miles per hour would make the most sense, but we're not talking about hours here, so we can't do miles per hour. So 25 units per second is how fast the truck is going. Okay. All right, the second question we're going to look at is the truck speeding up or slowing down? There's a common sense answer to this question, right? Probably slowing down. Now, but it could be speeding up if it was going like downhill and the brakes were broken. So there's a chance it could be accelerating. We're not sure. We're going to guess slowing down, but we want to show mathematically. Yeah. Yeah, you're going to take the second derivative because you're asking, if you're saying speeding up versus slowing down, you're talking about the rate of change of the rate of change. So velocity is your current speed. Velocity is your current speed. If they're asking how your current speed is changing, they're asking for the change of the change. Does that make sense? So this one is talking about your acceleration. Are you decelerating or are you accelerating based on the math? So we're going to go ahead and find the acceleration function, which is going to be the first derivative of the velocity, but it's the second derivative of the position. So we're going to take this equation right here and we're going to find the derivative of that.
Do we always have to write it down?
No, I'm just going to keep reminding you because you basically have to have those three things memorized. You got to know how they relate to each other. Yeah, I'll keep writing them. I'm a big fan of pointing out the obvious as I write. So I like that. Yeah. All right, so if I find the derivative of this, what do I get? Yeah, I got 0 minus 1.8t. You don't need the 0 there. If you want to just write minus 1.8t, you can.
Yeah, how'd you get that?
The derivative of 25 is just 0, and then the derivative of this I multiplied by the 2, and I dropped the exponent by 1.
Okay, thank you.
Okay, so with this, and we will talk about this more, but the trick to understanding acceleration, it's not just that this happens to be negative, although that would seem the case. Oh, it's negative, so you're going slower. Anytime your velocity and your acceleration model have two different signs, that's how you know it's slowing down. All right, and I will talk about that more in the next video, your video for tomorrow's homework, okay? So here we're just going to say it is slowing down, which makes sense. We would hope that as you exit the freeway that you are slowing down.
So what you said, like, what the
And I'll address it in a future video, but basically if the signs are different, if your acceleration is positive, or if the velocity is positive and your acceleration is a negative number, that means you're slowing down. If they're the same, it means you're speeding up. So 2 negatives would make a positive. 2 positives would stay positive. One of each makes a negative. Yeah. Yes? Okay, we got one last example to talk about. So the position of a particle of what? I don't know, dust or paint or something. So the position of the particle is given by this equation where t is in seconds T is in seconds, and S is meters. And the first thing we want to do is find the acceleration at time t. So find the acceleration at time t. All right. So what are we doing if they want us to find the acceleration? And they're saying at time t, so they're not saying plug a number in. They're just saying for any time I could possibly want to plug in, how do I find the acceleration? Second derivative. So we're going to say s of t, that's our first derivative. And then our second derivative, s of t was our original function. V of t is our first derivative. And then a of t is our second derivative. And I'm going to remind you of the units so that we know them for this problem. Position is meters. Velocity is meters per second. And then acceleration would be meters per second per second. Meters per second per second. Which we say is meters per second squared. Okay. So what we probably want to do first is just find the first derivative, because that helps us to find the second derivative. So V of t is what? Okay. And then a of t would be? Okay. So the acceleration at time t is just this. What is the acceleration after 4 seconds? So we're going to take 4 seconds, we're going to plug it in. What does that give us? 12 meters per second squared, right? So 12 meters per second per second. I would. I might not mark it all the way down, but odds are on this test I will give you 1 point for the number answer, 1 point for the units. So then you get a point off for not having your units in there. All right, next is find the velocity and speed after 4 seconds. So find the velocity and the speed after 4 seconds. So how do I find the velocity after 4 seconds? Yeah, so V of 4 is 3 times 4 squared minus 12 times 4 plus 9. Three times 16 minus 48 plus 9. What is 3 times 16? 48. So what is it? 9 meters per second. Now, velocity represents two things, if you've taken physics. Velocity is a speed, but also a direction. Yeah, you can go backwards with velocity. So here, when they're saying velocity and speed, that's not a redundant question. The speed is just the absolute value of whatever you get for velocity. All right. So if your speed or your velocity is 9 or -9, then your speed would be 9, just in general. Okay. So here our velocity is 9 meters per second. Our speed is also 9 meters per second. They match. So at 4 seconds, that's how fast the particle is moving. 9 meters per second. If your velocity was negative and then you set the speed, you would say positive. Yep. So velocity can be in the negative direction, but speed always is positive. Yes.
You say, okay, I'll run that hard. That's great. But that's what
All right. Explain. So explain what is happening to the particle at 4 seconds. So the particle is traveling 9 meters per second, and it is increasing speed at a rate of 12 meters per second squared. Okay? So we're going to say that the particle is speeding up because the position is increasing at an increasing rate. Does that make sense? So our acceleration was positive. So our speed is increasing, and it's doing it at an increasing rate. The particle is moving faster. Acceleration. So it's increasing, so it's going at 9 meters per second, and it's doing it in a positive direction, so it's increasing. And the increasing rate is 12 meters per second squared. Okay. So we're going to say it's accelerating. Okay. So the velocity is in the positive direction, which means it's increasing, and it's increasing at an increasing rate. The rate is getting faster and faster. It's accelerating. Okay.
Like a positive acceleration, does that make sense?
Kind of, yeah.
Okay.
Yeah. Because if you said that something was decreasing at an increasing rate, that would mean it's like going way slower, right? It's decelerating. All right. If you said something was decreasing at a decreasing rate, you'd be like double negative.
You'd be upside down.
Yeah, it's confusing. All right. So here we're going to say the particle is speeding up. And this is because the velocity and acceleration are positive. So it is increasing at an increasing rate. You might write that in your notes if you need to. It is increasing at an increasing rate. Well, they're just asking you to kind of sum up what you notice when you compare the velocity and the acceleration. Because
I shouldn't write that, or
you can write this.
no, but I'm saying, first of all, I already wrote it. But I can erase it. I'm just asking, like, if I wrote 9 meters per second.
You're good. Leave it. Leave it there. Yeah, leave it there.
You go to the side.
Okay.
Because that makes more sense, like, right exactly.
Okay. And then last, we're going to find the total distance. So find the total distance traveled in 4 seconds.
that's just like finding like the difference between all of them, right?
Yeah, so you in the past have done something where you found like the beginning position and the end position, and you just subtract them, right?
Yes.
That's displacement. That's saying it went from one thing to another thing. We're not talking about that. We're talking how far did it move, because it could go back and forth, and then we would count more than one thing. You know what I'm saying? Yeah, physics. So we're not talking displacement here. We're saying how far did it travel. So what we want to know is we want to know when the velocity was 0. Because if we know at what time the velocity is 0, we know when it stopped traveling. Does that make sense? We need to know at what time it stopped traveling. And then we can count. We can say from when it started traveling until when it stopped, that's some distance right there. And then from when it started to when it stopped again, that's another distance right there. And then when it started to when it stopped, that's another distance right there. And we can add up our distances. Okay? So we're not going to say starting position and ending position and subtract them, because we could be going back and forth. Yeah.
Can you say that in the context of the problem?
Say it again?
Can you say that in the context of the problem?
Yeah. So we're going to look at this problem. We're going to say we want to know when the velocity is 0. Because when the velocity is 0, that's when this thing stopped moving. Okay. So our velocity was 3t squared minus 12t plus 9, and we want to know when that equals 0. So how do I solve that? Factor. How can you factor it? So I can take out that GCF of 3, right? T squared minus 4t plus 3 t t minus 3 t minus 1. Darius, remember I'm videotaping this for you, right? Yeah, you're good. So no worries. All right. So what are the two different times where it stops moving? Okay. So what are the two times when it's not moving at all?
3 and 1.
Yeah. So at 1 second and at 3 seconds, right? Okay. So if we want to see what happens, we know that the particle is going to start moving at 0 seconds. So we're going to look at the position at 0, and we're going to look at the position that it's at 1. And we're going to look at the position where it's at 3 seconds. And we're going to look at the position at 4 seconds. And then when we compare all those positions, we'll be able to see how far it has traveled overall. Right? So we're going back to the position function to plug these numbers in. So if you go back, and I'll go ahead and write it down here so we can look at it. The position function was t to the third minus 6t squared plus 9t. So what do you get when you plug 0 in?
0.
You just get 0, okay. What do you get when you plug in 1? Yeah, so 1 minus 6 is negative 5. Negative 5 plus 9 is 4. What do you get if you plug in 3? What do you get? I don't think it's 36. 3 to the third is 81. This is hurting my brain already. Oh, 3 to the fourth is 81. Oh yeah. Okay, 3 to the third is. Let's go ahead and I'm gonna type it. I'm gonna type it and double check. 3 to the third minus 6 times 3 squared. It's 0. All right, and then if you plug in 4, we just did it. We already knew it was 0. Yeah. And then if you plug in 4, you get 4. Okay, so from 0 seconds to 1 second, from 0 seconds to 1 second, how far did you go? You went from 0 to 4, so you went a length of 4. From 1 second to 3 seconds, how far did you go? But if we think about distance, we're just going to say 4. Positive or negative, doesn't matter. It's just 4. And then from 0 to 4, how far did you go? 4. So how far did we go overall? 12 units. And here, did we say it's meters, right? 12 meters. That's how far it moved. Whew.